right here, 41.75 plus 37.5, and we got 79.25 inches to the fourth for our answer. Now, before we go on and calculate IY and IXY, using the table over here, remember this table is super helpful in getting all the values that we need to do the parallel axis theorem. But before we go on, I want to talk about this in application to reality for a second. I mentioned that this is the floor slab in buildings like Marcus Hall and Coors Tech Center, all those pictures that I've shown you this semester. That's that concrete slab in there. That number we got for IX, 79.25, that is a number that we would use to calculate how much that slab is going to sag down, how much it's going to do this when we get students or whatever other kind of load into those classrooms there. And so that's a number that we can take to the bank. Now, one of the things that's really cool about this system is, and this is really bonus material, the reason we get a T-shape out of this is because the forming that they use is shaped like this. It actually isn't quite a T. We ignored the little triangles there for our class example here. So we just basically, our slab, the cross-section of the slab actually looks like this. Well, what we did is we pulled out a T shape out of there like that. Well, the really cool thing is that if we have this 5 inches right here, and that's what our example was, we had the 3 inches over here plus 2 inches, so we had a total thickness of 5 inches. Well, by doing this T shape, the actual equivalent area, or not area, but the equivalent volume of concrete is for that of a 4-inch slab. And concrete is not very environmentally friendly. It emits tons of carbon into the atmosphere when you're producing concrete. So if we can reduce the volume of concrete from 5 inches down to an effective 4-inch slab, we're reducing the volume by about 20%. That's a significant savings, right? Now, the cool thing, though, is that even though we're reducing the volume down, we're getting the strength from a 5-inch slab. We're getting the stiffness of a 5-inch slab. And I want to point out specifically, look how much stiffness we get out of this top rectangle. The top rectangle was rectangle number 2. IX2, we get 37.5 inches to the fourth. IX1, this little area down here that's sticking down, we get 41.75. So we are like more than doubling the I just by having that little piece sticking down there. And so we're reducing the volume of concrete while keeping basically the strength of a 5-inch slab. That's why this stuff is so popular to use in buildings, because it's a very efficient and effective system. Okay, let's go ahead and move on now. We calculated IX, and now we would do the same thing for calculating IY. If we want to find IY, and I'm not going to go into a lot of details, but we would do IY1 would be equal to IY prime 1 plus A1 times the distance between the Y axis and the Y prime axis, and that's a dx distance, so dx squared. We would do IY2 would be equal to IY prime 2 plus A2 times a d sub x2 squared. And so all those values live in our table over here, so we can find this IY1. IY1 is just going to be our table over here. That would be 20.83. IY prime 2, that would be our table, 432. We can find A1, A2. We do all that. I just want to reiterate here that we have to figure out the moment of inertia for each area before we add them together. Then we can take our IY1 plus IY2. And when we do the math here and we plugged it in, we would end up finding 0.83 inches to the fourth. Now, when they're designing those buildings, they're probably not using IY at all. Iy would be if we had forces that were pushing on the side of the slab. Ix is for bending about that x-axis, so that's for our downward forces. That's for those forces we think about when we're getting the slab is doing this. Iy would be if the slab was bending in this direction, so kind of coming in and out of the out of the screen here, out of my video. So we usually, the slab systems are not the ones that support the lateral loads in a building. They can, but typically the slabs are only for vertical loads, and so that's why we only used Ix. But for our example, we'll calculate Iy as well. Now, how about Ixy? Ixy, same idea. Ixy1 is going to be equal to Ix prime y prime 1 plus a1 times d sub x1 times a d sub y1. And so we can plug in our values for there. Now, nowhere in our table did we write what Ix prime y prime is equal to. Let me call somebody from the front row. Prash, I see you've got your camera on here. You're in the front row today. Do you remember what is for Ix prime y prime 1? Now that, just to remind you here, that would be, if we go to our picture on the left there, that's the product of inertia for just this A1 rectangle about the centroid of that rectangle right there. Any ideas what that's equal to?
Would that be equal to 0?
That's right. Absolutely. That's equal to 0. So it shows up in our equation, but it's equal to 0 because we have symmetry on the x prime, y prime axis. So we have symmetry on x prime, y prime for A1, right? So for the centroid of just A1, we're going to get 0. So we have 0 plus A1, which is 10, times dx1, which is, oh, that's also 0, and dy1, which is also, well, dy is minus 1.96, but it really doesn't matter because dx is 0. So we find ixy1 is equal to 0. And then what do you think we're going to find for ixy2 then? It would also be equal to 0 because dx is 0, because ix prime y prime 2, so ix prime y prime 2 is 0, but also dx2 is 0. And so we end up with ixy2 is 0, which means that ixy for the whole thing is equal to 0 as well. So and the reason that it's equal to 0 is because don't we have symmetry on the y-axis about the whole thing? We have global symmetry on the y-axis. So I would write it down right next to where I just wrote ixy is equal to 0. We have global symmetry on the xy, or not the xy, but on the y-axis. So ixy should be equal to 0. That's when we have ixy is equal to 0. Remember, ixy is equal to 0 when we have symmetry on the x, the y, or both. And then what does that mean? That means that the ix and iy are principal moments of inertia. Principal moments of inertia means max and min. Now it doesn't, ixy being equal to 0 doesn't tell us, but which one is maximum? Iy is bigger, right? We can just look at these. So Iy is equal to I max and Ix is equal to I min. Just by observation is all we're doing here. To figure that out is just by observation. So anytime we have symmetry about those axes, it's going to be 0. Any questions about that example?